This is part 2 of my lecture on the sun, in which I'll describe what we think is happening inside the sun. As I mentioned in the last video, the sun is a big ball of gas. It's not solid. What's keeping it from expanding and contracting is that at every spot in the sun, there's a perfect balance between the inward pull of gravity and the outward push of pressure. This is called equilibrium. At some point in the very distant future, the equilibrium will be broken and the sun will do all kinds of interesting things before it finally dies. The light we get from the sun originates deep inside the core. It results from the fusion of hydrogen into helium. The mass of the helium that's produced is slightly less than the mass of the hydrogen that went in. That excess mass is released as light and other forms of energy according to Einstein's famous equation, E equals mc squared. There are two main types of nuclear reactions. When two light nuclei combine, they form a heavier nucleus. That's called fusion. When a heavy nucleus splits apart, that's called fission. Humans have figured out how to do both. Our nuclear power plants generate energy through fission. They split heavy nuclei, such as uranium. The only nuclear bombs that have been dropped on people at Hiroshima and Nagasaki were fission bombs using uranium and plutonium. We've also developed and tested hydrogen fusion bombs, but thankfully haven't used them in conflict. We've also not yet used hydrogen fusion as a source of power. There are experiments underway that hope to make fusion power a reality in the next decade or two, which I'll describe later in the video. The fusion process that takes place in the sun is called the proton-proton chain because it's a chain reaction that starts with two protons. As I said in part 1 of this lecture, the sun is mostly hydrogen, and hydrogen always has one proton. Elements are named according to how many protons they have. The name doesn't tell us how many neutrons or electrons there are. The blue particles shown on the diagram here are protons, and they're labeled H1. H is the chemical symbol for hydrogen. The number above and to the left of the chemical symbol is called the atomic mass number. That's the number of protons plus neutrons. So H always has one proton, and H1 is one proton and 0 neutrons. Normally, two protons will not stick together because they both have a positive charge. They will repel each other. There's only one force in the universe that can overcome this electromagnetic repulsion, and that's simply called the strong force, or sometimes the strong nuclear force. The strong force only operates on the tiniest scales though. If you can bring protons together for a brief instant, then the strong force will take over and hold them together. So what needs to happen is that protons need to be moving really fast and to collide frequently. At the macro level, we call that high temperature and high pressure. The only places in the universe that are hot enough and dense enough for this to keep happening over long periods of time are the cores of stars. Now let's look at the reaction that's shown on the figure here. Two protons smash together and one of them gets turned into a neutron. That's the red particle. The nucleus that consists of the blue and red particles stuck together is still hydrogen because it still has one proton, but it's H2 because it's one proton plus one neutron. A couple of other particles are also produced in this reaction. One of them is a neutral particle called a neutrino. As its name suggests, it's like a little neutron. It was jokingly named neutrino by Enrico Fermi and another Italian physicist. I'm sorry, one time I was in Italy with a friend of mine who was from there, and I kept trying to speak like them, and they said I sound nothing like them. Neutrinos are the most penetrating particles known. They go right through the Earth. So they go right through your body as well. Every second, trillions of neutrinos produced in the core of the sun pass right through your body. The other particle produced here is a positron. It's an example of antimatter. It's the anti-electron. It's the antimatter counterpart of the electron. It's called a positron because it has a positive charge. An electron has a negative charge. When a particle and its corresponding antiparticle come in contact with each other, they both get destroyed, and their masses get turned into energy in the form of light. So what do you think happens to this positron? Post a comment about it. The hydrogen 2 from step 1 will then smash into another proton and stick to it, forming a nucleus consisting of 2 protons and 1 neutron. This is now helium. It's helium because it has 2 protons. And its symbol is He3 because it's 2 protons plus 1 neutron. This reaction also releases a gamma ray, which is a high energy photon. So some of the light we get from the sun originates in step 2 of the proton-proton chain. Then in the third and final step of the fusion process, one of these helium-3 nuclei combines with another one just like it. So here's another question for you. How do you think the second helium-3 nucleus was produced? Post a comment about that. When these 2 helium-3 nuclei smash together, 2 protons and 2 neutrons stick together to form a helium-4 nucleus. It's still helium because it has 2 protons. It's helium-4 because it has 2 protons and 2 neutrons. The remaining 2 protons are released. So here's one more question for you. What do you think happens to each of those protons that gets released, that doesn't stick to the nucleus that's formed? Post your response about that as well. So this is the complete proton-proton chain, which is the main process by which hydrogen gets turned into helium in the core of the sun. On the discussion board, I'd like you to list all the inputs and outputs of this 3-step process. It might seem complicated, but you just have to go through these last 3 slides and list what went in and what came out. The sun has been generating energy through hydrogen fusion for 4.5 billion years. When the sun was born, it was 90% hydrogen. All of it except for the core is still 90% hydrogen, but nearly half of the hydrogen in the core has been fused to make helium. There's enough hydrogen in the core to keep this process going for another 5.5 billion years. So clearly, hydrogen fusion is one of the most efficient and sustainable energy production mechanisms in the universe. That's why we'd like to do this here on Earth. Of course, it's not at all easy. There's no way to create the enormously high pressures that are found in the core of the sun. That means we need even higher temperatures than what's found in the core of the sun. We have been able to do this for a brief instant in some of our high energy particle labs and in the hydrogen bombs we've tested, but to use it for hydrogen fusion, to use hydrogen fusion for power generation, you need to keep the fusion reactions going. It needs to be sustainable and it needs to be safe. There are a couple of projects underway to do that. The biggest one is an international effort called ITER. The reactor is being built in France. The member countries are the European Union, the US, China, India, Russia, Japan, and Korea. It might start operating as early as 2025, but will need to run for 10 years before it can start fusing hydrogen into helium. At that point, the energy coming out should be 10 times as much as the energy that's required to run the reactor. So 50 megawatts go in and 500 megawatts come out. 500 megawatts is decent, but it's still modest for a power plant. Today's largest power plants and our hydroelectric dams can generate many times that. And here's the great irony. The power that's generated by ITER won't actually be stored and used. ITER's goal is just to demonstrate that fusion power is possible and feasible. If it succeeds, then presumably the member countries and possibly other countries, and maybe even private companies, will start building large-scale fusion power plants. There are a couple of companies now that are trying to do this on a much smaller scale, using different mechanisms and different technology. Coming back to the sun, the helium that's produced in the fusion process stays in the core. I've asked you what happens to the positrons, which again are anti-electrons. The neutrinos go right through the sun and escape into space. Light particles, also known as photons, don't escape so easily. They keep getting absorbed and scattered by the hot gas in the sun. As they do that, they lose energy. This is how the continuous portion of the sun's spectrum is produced. The sun's spectrum peaks in the visible and infrared and drops off at higher and lower energies. The light produced in the core of the sun isn't visible or infrared light. It's actually gamma rays. But those gamma rays don't make it out of the sun. In fact, they don't travel very far before they get absorbed by hot gas and often re-emitted as multiple lower energy photons. So one gamma ray photon goes in, gets absorbed, and then that atom will eventually emit one or more photons. And if it emits multiple photons, each of those will have lower energy than that gamma ray that got absorbed to begin with. And then those photons that got emitted will get absorbed by some other particle and then get re-emitted and so on. So the more interactions there are, the lower the energy of the photons that ultimately get out of the sun. On average, there's around 1 million years between a photon being produced in the core and one of its descendants finally making it out of the photosphere. Of course, after that, it'll take just 8 minutes to get to the Earth. Outside the radiative zone, there's a layer where hot gas rises and cool gas sinks. This process is called convection. And so this layer is simply called the convection zone. While we can't see what's happening in the core or the radiative zone directly, we actually see the convection happening just beneath the photosphere. The photosphere has texture, which we call granulation. Each of the granules is actually a convection cell. If we zoom way in and then watch the sun over time, if we take a video of solar activity for about an hour, then within that hour, we'll see bubbles appear and disappear. So we have direct evidence of a convection zone beneath the photosphere. Other than that, we have several indirect ways of studying what's happening inside the sun. One of them is similar to how geologists use seismic waves, such as those produced in earthquakes, to study what's happening inside of the Earth. What's shown on the figure here are alternating blue shifts and red shifts on the photosphere of the sun. The sun is throbbing or pulsating. We can observe these vibrations and then try to reproduce them in our computer simulations of the sun's interior. So basically we see the outside, and then based on what we see outside, we try to make a model of the inside. And finally, we have the neutrinos that are produced by the fusion process in the sun's core. Since they go through just about everything, they're incredibly hard to detect. All of the normal matter we usually encounter is made of protons, neutrons, and electrons. And we see normal matter because of the way it interacts with light. Neutrinos don't interact with protons, neutrons, electrons, or light. They don't absorb, reflect, emit, scatter, or interact with light or any normal matter in any way. But there is one thing a neutrino will interact with. I'll give you a few seconds to try to figure out what that is. This time I don't want you to post the answer. I will give you the answer. The one thing a neutrino will interact with is an antineutrino. If a neutrino and an antineutrino come in contact with each other, they'll destroy each other and produce two particles of light. Here is a picture of a neutrino detector deep underground in an old nickel mine in Sudbury, Ontario. It's basically a large clear bowl filled with a special type of water called heavy water and 9,600 cameras outside looking in. Heavy water has a couple of extra neutrons than normal water. Apparently it looks like water and feels like water, but I don't know if it tastes like water, and I don't want to know because it's not safe to drink. But the extra neutrons in the heavy water will decay, and when they do, they produce antineutrinos, which then come in contact with the neutrinos from the sun. The cameras don't see the antineutrinos or the neutrinos directly, but they do detect the light that's produced when the neutrinos and the antineutrinos annihilate each other. That's what the cameras are for. They just sit there, they're always on, and they just see flashes of light appear out of nowhere inside this fishbowl, and from the energy of the light that's produced, they can tell what did it. And this is deep underground, so there should be no other particles around. There should be no interference from any other particle. So they should only be seeing light of one particular frequency, which is produced when a neutrino annihilates with an antineutrino. The Sudbury Neutrino Observatory was built to solve what was called the solar neutrino problem. There are actually three types of neutrinos, but the proton-proton chain, which I described earlier, only produces one of them, and that one's called the electron neutrino. There were electron neutrino detectors before this one, but they didn't detect nearly as many electron neutrinos as we expect from the sun. That was the problem. The sun should be emitting so many electron neutrinos. They should go right through the sun because they don't interact with anything in the sun. They shouldn't interact with anything in the 93 million miles between us and the sun. And we should detect so many neutrinos per second within a square meter. But we weren't detecting nearly that many. One of the potential solutions to this problem was that neutrinos can change from one type to another. Some major theories of particle physics predict that in the time it takes neutrinos to travel the 93 million miles from the sun to the earth, some of them should have changed to one of the other two flavors. If that's true, it's a big deal because it means neutrinos have mass. The reason for that is quite deep. I think some of you will find this fascinating. Stay with me. According to Einstein's special theory of relativity, no particle can travel faster than light. And any particle that travels at the speed of light can't have mass. So photons have no mass, and if there's any other particle that travels at the same speed as a photon, it also can't have mass. The more massive a particle is, the less fast it can go. And here's where things get strange. When you travel close to the speed of light, time slows down. The faster you go, the more it slows down. And if you get to the speed of light, time stops. So particles that travel at the speed of light don't experience time. There's no before or after for them. For us, a photon appears to take 8 minutes to get from the sun to the earth, but from the point of view of the photon, it didn't leave the sun and then later get to the earth. Time doesn't exist for photons. How about neutrinos then? If they change from one type to another, then obviously there's such a thing as a before and an after for a neutrino. That means they don't travel at the speed of light, and that means they have mass. Unlike its predecessors, the Sudbury Neutrino Observatory could detect all three neutrino types, not just the electron neutrinos that are produced in the sun. And it did detect all three types, and when you add together how many are detected at any given time, it exactly equals the number of electron neutrinos that we should have gotten from the sun. So besides telling us what's going on at the core of the sun, neutrinos allow us to test out theories about the fundamental particles and forces that make up the universe. So there's a lot of neutrino research going on now throughout the world because this tells us basic things about physics. This concludes my lecture on the sun.